So a summary of what we said so far is as follows. We can use direct proofs, proof by contraposition, not Q implies not P, proof by contradiction, P and not Q, and we lead to a contradiction. There are some trivial and vacuous proofs, but they are usually not that important. And we can use constructive or non-constructive existence proof. Just about constructive and non-constructive, do you remember the example? The whole idea is being able to find genuinely this square root of 2. So that when you put square root of 2 to the power square root of 2 and square root of 2, you put them one to the power of the other, then you get rid of, you get finally a rational number. But still, we could not use this as a direct proof. I mean, it's not a proof of the existence of such a number, which is square root of 2 and square root of 2 to the power of square root of 2, because we don't have a guarantee that this number here is rational or irrational, okay? The assumption was if you have two different irrational numbers, okay, then x to the power of y must be, can be actually rational, okay? And we know that square root of 2 is irrational, but we don't know whether square root 2 to the power square root of 2 is rational or not, okay? So this is why we had to proceed in a different way, okay? Good. In this section, we'll investigate more proof strategies to prove different forms of arguments or theorems. And you will see that they fit within one of the first three types. So you will be using a proof by case to make a direct proof, or to make a proof by contraposition, or a proof by contradiction. Just because your elements X that you are proving a certain property or disproving a certain property for them, they are of three different types. Okay, they are positive, negative, or equal to 0. Okay, so this is the proof by case. Sometimes your property, the conclusion seems very awkward. Okay, there is nothing that related to the original assumption. The original assumption is for any positive number, okay, you have a very complex property on top of it, okay? So, but since it's complex, maybe if you start analyzing it, you will reach at the end that n must be necessarily greater than 4. But when it's greater than 4, then n is positive at the same time, okay? And then you can make your proof forward, okay, but after you analyze the conclusion and getting backward to the original premises, okay? So you will see these types of or methods of proofs in this deck of slides. So the first one is proof by case. We assume that we want to prove a conditional statement of the form P implies Q. In case P is the disjunction of different cases, then this means that P is something like P1 or P2 or Pn. And if you are interested in proving that this implies Q, then it means that you should prove that P1 implies a Q and P2 implies a Q, and so on and so forth, okay? We can show very easily in logic that those two lines, the last two lines, okay, the formula on the last two lines are 100% equivalent, okay? A or B implies C is equivalent to A implies C and B implies C, okay? So once again, it's sufficient to have clouds or some extraordinary phenomenon to, I don't know which is maybe a nuclear bomb, to have rain, okay? Either artificial or natural rain, okay? Well, it means that clouds alone are sufficient, and the atomic bomb alone is sufficient to have rain, okay? Good. So in this term, we have to prove that Pi implies Q for every I. Let's check one example. So before that, just one word. An exhaustive proof in this case would be a proof for all the cases, okay? But sometimes you can also use the without loss of generality trick to say that in some of the cases they are actually dual, they are the same, okay? So without loss of generality, we prove case 1, we prove case 2, and then without loss of generality, case 3 is the same, okay? So for example, you have two integers, they could be equal, or one of them is greater than the other, okay? So either x is equal to y, or y is greater than x, and without loss of generality, we don't have to prove it when x is greater than y, if x and y, they are playing the same role in the theorem, okay? Because it's just another, it's the dual, it's the same thing. It won't change any case. And exhaustive proof would be used when the number of cases is reasonable. So when you have, for example, the let's consider the example. We have this property, and we want to prove it for all integers that are less than or equal to 4. For all positive integers that are less than or equal to 4. So how many n do you have? 1, 2, 3, and 4. Okay. So here in this case, you can make an exhaustive proof. You replace n by its value, and you can do it. Okay. Okay. Otherwise, you can proceed with general cases. Okay. As we shall see. So in this case, you can do the proof on your own. A proof by case could be something like this one. Show that n squared is greater than or equal to n whenever n is an integer. So how do you proceed? And we mean by an integer any element of z. So it could be positive, negative, or equal to 0. So how do we proceed? Yes. Yes, sure. Okay, and then you get. But do we have this true for or it could also be 0 in this case? Okay. Yeah. So there are 3 possible cases actually. So n is equal to 0. So don't forget that we have n squared is greater than or equal to n. Okay. So we can consider the case where n is equal to 0, straightforward. N is greater than or equal to 1. Okay. And this is what you just proved actually. In this case, n times n is greater than or equal to n times 1. Okay. And if n is less than or equal to minus 1, okay, in this case, n is negative actually. So n times n is less than or equal to, actually, when you multiply by n, once again, n is negative, okay? So it flips the less than or equal sign. So n times n in this case becomes greater than or equal to minus 1 times n, okay? Which makes it, once again, positive, okay? Is it fine? So proceeding by case makes it easier for you. Like I knew that with I know that with the backward proof kind of that you were trying to do, okay, you were analyzing the property and you were showing that it holds, okay, but it only holds for the one of the cases, okay. If you proceed by cases, then you make an irrefutable proof. Yes, complete proof. Yes. We are just. Uh, we didn't do this actually when for any n greater than or equal to 1 included. So for any n greater than or equal to 1, the n is greater than or equal to 1. So n times n is greater than or equal to n times 1. Yes, yes, but it's simply because very easy. It's very easy to prove in this case. Okay, you just consider the range for n. Okay, and with only one step by multiplying by n, you can prove your property. No, exhaustive cannot be an exhaustive proof cannot be done here because the set n is yeah, it's countably infinite. Okay, you can count all the numbers in it, but it's infinite, still infinite. So you cannot prove it for every single instance. Okay, but when you have a finite set, then you can prove it for any element in it with an exhaustive proof. Okay. Okay, good. So another example where a proof by case is really maybe the only way to proceed to prove a certain properties on absolute values. For example, the absolute value to prove that the absolute value of x times y is equal to the absolute value of x times the absolute value of y. How would you proceed? Okay, though there are yeah, yes. Mm-hmm. 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 Absolutely. Okay. Do you see? So it depends on the signs of x and y. Okay. If both of them are positive or both of them are negative, or one of them is positive and the other is negative. Okay. And actually, this is the only third case. Okay. But if you reason about it in terms of x and y, so it could be that x and y are greater than or equal to 0. It does not cause any problem to have 0 in one of these cases, okay, because they are in this case equal, okay. Strictly negative, x and y strictly negative. We could also consider less than or equal to 0, less than or equal to 0 on both sides, but it's not really required. خلاص, we already considered. And we could have them of different signs, okay? Okay, so, but if you work technically, if you do not analyze your formula completely, well, actually, we are missing a certain case, which is when x is less than 0 and y is greater than or equal to 0. Okay, but we know that without loss of generality, and because the multiplication operator is commutative, so the absolute value of x times y is equal to the absolute value of y times x. Okay, and absolute value of x times absolute value of y is equal to absolute value of y times absolute value of x. Okay, so once again, because multiplication is commutative, so we can x and y play dual roles, okay, similar dual roles for each other. Okay, so this is why step number, actually case number 3 and 4, they are the same. Okay, and I think you can show it very easily why it holds in all these 4 cases, and this makes it always true. But before proceeding by case very carefully, we cannot just say, yeah, it seems very intuitive, very obvious, okay? So you just have to do this one single step, okay? The same can be done when you work with the ceiling and floor functions. You know, like, do you know these functions? The ceiling of a certain number x is equal to x if x is an integer, or to x plus 1 otherwise. Okay, so to the floor of x plus 1. Okay. So typically with those functions, you can state wonderful properties, okay? But to prove them, it really depends on, for example, on if you consider the sum of 2 different numbers and the sum of their ceilings or floors. So it really depends whether x is equal to a certain integer perfectly, or it's an integer point 2.3 up to something 0.5, or it's like 0.6, 0.7, something that is above the half. So when you sum them up together, okay, if I consider 1.2 and 2.4, okay, so it remains something like 3.6, okay, which is still below 4, okay. But if you consider 2 numbers that have fractions above 0.5, then you get a bigger number, okay. So you exceed 4, you get 4 point something. So and here, like, you also need a proof by case, okay, just to show you. It depends on your exercise, but in the worst case, something like less than half, greater than half, okay, and a full integer, okay, yeah. Ah, no, it's not. Well, actually, each case cannot be proved by instantiation, okay, because we have to prove it for every x greater than or equal to 0 and for every y greater than or equal to 0. Okay, so here you get back to a very basic proof. Okay, for example, a direct proof works here. So you know that x times y is positive, so the absolute of x times y is equal to x times y normal. Okay, the absolute value of x is equal to x, and the absolute value of y is equal to y because both of them are positive. And here I have a very obvious equality of x times y is equal to x times y. Okay, but I proved it for any x and for any y that are both greater than or equal to 0. Okay, I cannot just show that 4 is equal to times 2 is equal to 4 times 2. Okay, it does not work in this way. Okay. Well, with exhaustive proof, you as with the example for any positive number that is less than 4, okay, if you prove it for 1, 2, 3, and 4, then it's sufficient. So why to bother and to prove the property for engendered, okay? And just show that the property is respected as long as the number is positive and less than 4. It's a burden to do it. So just do it exhaustively for all the values 1, 2, 3, and 4, and that's it. Okay? Yes. No, you don't give examples, but you have to play on the mathematical property or definition of the absolute values, and to show that if you start from the right-hand side of the equality, okay, then you get to the right, okay, you can get to the right-hand side of the equality, and vice versa, okay? You are showing that two mathematical formulas, they are equal, okay? Or you can analyze the first one, as I did just earlier, okay? I analyzed absolute value of x times y, I get rid of the absolute value, and I analyze absolute value of x times absolute value of y. I could get rid of the absolute values, and I showed that finally they are obviously equal. Okay, they can be rewritten as simply x times y, y and x times y from the other. So they are equal. Yeah. So would you like to do it for the second line, for example? So when both of them are negative, x times y is positive. Okay. So in this case, the absolute value of x times y is equal to simply x times y. And since x alone is negative, so absolute value of x is equal to minus x. And absolute value of y is equal to minus y. So absolute value of x times absolute value of y is equal to minus x times minus y, which is equal to x times y. So once again, I could prove that these both parties of this equation are really equal. Yes. Yeah. The details of every case. Yes, you have to show all the details of every case. Here we are not giving this on this slide, okay? But usually a proof by case does not end here. It's just first part, okay? A first step, identifying the possible cases, okay? And why did we identify those cases? Just because they really influence the values of these absolute values, okay? So, and we want to get rid of them actually to be able to get to some basic mathematical fact, yes. The exhaustive proof here. Yeah. And third, yeah, when n is greater than or equal to 1, okay, then it means that n is also positive at the same time. Okay, this implies that n is greater than 0 strictly. Okay, so if you multiply both parties, okay, of the inequation, n is greater than or equal to 1, okay, which is your original fact in this case, you get n times n must be also greater than or equal to 1 times n. Okay, okay, and this makes n squared greater than or equal to n. Okay, good. Now you still have to prove it for the third case. Okay, but here you play on the sign of yeah, the third one, yes. So n is less than or equal to minus 1. Okay, this means that minus n, okay, is greater than or equal to 1. Okay, and this gives you that n actually times times n is greater than or equal to, once again, to 1 times n. Okay, so which gives you the same reality, like that n squared is greater than or equal to n. Okay, okay, yeah, yes, yes. Which one? The absolute value. Okay, sure. So for example, the second one, okay? Let's do it on one note. So it's all about playing on the definition, guys, of these formulas. So if x is strictly less than 0 and y is strictly less than 0, then by definition, the absolute value of x is equal to what? To minus x, okay? And the absolute value of y is equal to minus y. Okay, what about x times y? X times y is positive, okay? So in this case, the absolute value of x times y is equal to what? To x times y, very simply, okay? This is on one hand. On the other hand, absolute value of x times absolute value of y is equal to what? Minus x times minus y, which is equal to x times y times minus 1 times minus 1, so which is x times y, okay? So so you see, like you need, so it's a very sound question. Yeah, when you proceed by cases, it's not done in the slides, but you have to go to the end of your proof, okay? Good. So I think, yeah. A nice example is to formulate, first of all, a conjecture about the rightmost digit of a perfect square number, and then prove it. So it's a tough question if you were asked to think about it, but one way of doing this is to draw out this list, actually. The perfect square of numbers, square of 1, square of 2, square of 3, and so on and so forth, are as follows: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'm just focusing on the first number, okay? So you see 1, 4, 9, 6, 5, 6, 9, 4, 1, 0, 1, 4, 9, 6, 5, okay? So it seems as if the first digit belongs to a subset of the digits that we know, okay? So we were able to have 0 as the first digit, 1, 4, 5, 6, and 9. But none of them is 7. None of them starts with 8 or 6, okay? Do you agree? So it seems to be only 0, 1, 4, 5, 6, and 9. But now we have to prove it, okay? It could be wrong, but just let's give it a try. Okay? Okay? Good? So let's formulate the conjecture first. So the final decimal digit, or the rightmost digit in a perfect square is one of those values. How can we prove this? So we can actually prove it by case. Okay? Do you agree? Well, how? Whatever your number is, let's write it as 10a plus b. Okay? So whatever integer you consider. So how to write 1 as 10a plus b? You will see. So it's 10 times 0 plus b, okay, plus 1. Okay, so for a equals to 0 and b equal to 1, I can represent 1 as 10a plus b. I can do it also for 2, 3 up to 9 in the same way, a being 0 all the time and b is equal to 1. What if the number is 19, for example? Well, piece of cake. A equal to 1 and b equal to 9 or 3 or 2, okay, and so on. What if the number is bigger than 100 or 200? Okay, so it's not a big deal. We just want to isolate b, okay, the last digit. We want to isolate it in a certain way, okay, so we want to write it as 10 times certain big numbers. Let's say 256. 256 is equal to 6 plus times 10, okay, 25 times 10, okay? So we don't care if a becomes very big, okay? We just want to actually get to explicit in our formula here, in our number, the rightmost digit, okay? So the remainder of the division by 10, by the way. The b is equal to the remainder of the division by 10, yes? So in this case, B can only be what? 0, 1, 2, 3, 4, up to 9. Okay? And then we can do a proof by case, even by exhaustive cases. Okay? So we can check all these B's. We already did it on this slide. We drew out all the perfect powers, even up, further than 10, okay? Further than 9, okay? So perfect square of 0 is equal to 0. Perfect square of 1 is equal to 1, 4, and you see? So for no matter what B is, n squared in this case would be equal to 10 times a square, which is 100a squared, plus 20ab, and this number has 10 in it, so it cannot influence the final digit, plus b squared. Okay, so what gives you in the final number n squared the rightmost digit, okay, is b squared itself. Okay, because the first one is divisible by 10 and the second one is divisible by 10. So this is equal actually to 10 times 10a squared plus 2ab. Do you agree? Plus b squared. So the rightmost digit is there in b squared, and it's a constituent of b squared. And b squared can only have one of those numbers in it, 0, 1, 4, and so on and so forth. Okay? Is it fine? So now we show that the last digit in B2 can only be either 0, 1, 4, 5, 6, or 9. Okay? Yes. Just to explicit the last digit, B would be the last digit in n itself. Okay? It would be the last digit. Now, calculating n squared shows you that the rightmost digit in n squared is influenced by the value of b squared, okay? Because it's equal to 10 times something. It's actually 10 times 10a squared plus 2ab, okay? Okay? So, sorry? Because you get the rightmost digit when you divide by 10. Okay, so if I want to check what is the rightmost digit of 253, then I have to divide by 10. Okay, well, it's actually equal to 25 times 10 plus 3. Okay, and if I calculate this square, well, this is equal to 25 times 10 square plus 2 times 10 times 25 times the 3, okay? So I have 10 here, okay? So this number would be something 50, something 30, okay? So it won't have a digit in it at the end. This one neither, because it has hundreds in it, okay? And the only part that influences the final outcome is 3 squared, which is nice. So my number must necessarily end with 9 in this case, okay? The perfect square of 253 must necessarily end up with 9, and it cannot end. So if you do this for all the other numbers, like even 7 squared is equal to 49, which ends with 9. 8 squared is 64, so it ends with 4, and so on and so forth. Yes. Yeah, you can show it for every value of b, and the possible values of b are 0, 1, 2, up to 9, the simple digits. Okay, so for all of these values, okay, up to 81. Okay, so on the previous slide, we could just stop at this phase here. So up to 81. Okay, because even here the number 10 is 1, 0, so it ends with the 0. So it will end with 0 finally, 0 squared. Yeah. Because any number that you have 10,250 or 86, so finally it ends with 6. Okay, so any number you pick, it will only end with 0, 1 up to 9. Okay, these are the 10 possible values for the first digit. Okay, and since the square of this number, okay, the rightmost digit of the square of this number only depends on the square of the first digit in it. Okay, and the first digit in it is only one of those 10 possible cases, then it is sufficient to check exhaustively those 10 possible cases. Okay, and how to check them? Well, you draw out all the perfect square of them. Okay, good. The without loss of generality, like we already talked about them. Okay, for instance, here when you have to check the case where x is positive and y is negative, well, honestly, this is exactly the same as checking the case where y is negative and x is positive. It's simply the case where they have opposite signs. Okay, without loss of generality, we can prove it only for. We have to prove it for one of them. Okay, so but it's sufficient to consider, let's say, the first one where x is positive, y is negative, and then you can say for the case number 4, this is the same as case number 3 without loss of generality. Okay, but you have to be very careful once again because you're making a shortcut here, so you really have to be sure that the these two cases are really equivalent. Yes. But you just say one word about it. Without loss of generality, we can prove it also for the case where y is negative and positive and x is negative. Okay, good. Good. So in general, when the phrase without loss of generality is used in a proof, we assert that by proving one case of a theorem, no additional argument is required to prove other special cases afterwards. So of course, incorrect use of this principle can lead to unfortunate errors. So use it wisely. Do not abuse this rule. So sometimes assumptions are made that lead to a loss in the generality. Example, show that if x and y are integers, and both x times y and x plus y are even, then both x and y are even. How would you proceed? Mm-hmm. So yeah, I agree that if we we can do it by contraposition. We imagine that x and y are odd, okay, and then this must lead to the fact that either x times y is odd or x plus y is odd. Okay, so pay attention. If you want to proceed by contraposition, then proving that x times y is even and x plus y is even implies both x and y are even, would consist on of it doing it by contraposition would be as follows. If x or y is odd, okay, it means if x and y is even is false, this means that either x or y is odd, then necessarily x times y is odd or x plus y is odd. Okay, so maybe you can do it this way. Okay, maybe you can do it in all the typical methods, but I think this example here is just to show you a quick hint about the without loss of generality. Okay, the use of without loss of generality. So suppose that x and y are not both even, so one of them is odd. Without loss of generality, we assume that x is odd, so that x is equal to m plus 1. Okay? So it may seem for you a good step at the beginning because we don't need to consider the case where y is odd. Okay? Because they are playing a dual role. Okay? But do you see any problem in this case? Okay. So we also need to make certain assumption about y. Okay. So I agree with you. We should not consider also the dual case where y is odd and x can be whatever it wants. Okay. Yeah, but here, even if we fix that, let's suppose that x is the odd number, x is not the even number, okay? But you still have two different cases to check with this one. Either y is odd or y is even, okay? And you have to prove your property for both cases, okay? You cannot ignore that y can be any one of them, okay? Because just the fact that x is odd is already sufficient to refute that both x and y are even, okay? And now to prove your property, you have to consider whether y is odd or y is even, okay? So just one example of how you can go quickly with without loss of generality as a shortcut. So now we show that x times y will be odd or x plus y would be odd. So we have to consider two cases. Y is even and y is odd. Okay, good. In case y is equal to 2n, then x plus y can be written as something that is a multiple of 2 plus 1. Okay, and this means that the summation of x and y is odd. Okay, good. In the second case, the multiplication can be proved to be odd at the end. So you have 1 in it at the end. Good. So does this conclude the proof? They are the same. Okay. So the only remark that I gave is to check the possible cases for y. Okay. But now that you consider x is odd, y is odd, or y is even. Okay. Since your properties only consider addition and multiplication, well, the rule of x and y are dual. So actually, without loss of generality, you can assume that you concluded your proof. Okay. If you consider, yeah, right now it's fine. Okay. The problem was when we didn't consider the two cases of y, actually. Okay. That when those are even, okay, both of them are even, then necessarily both x and y are even. Okay. How did we prove? We proved it by contrapositive. Okay, we proved it by contrapositive by showing that when any of x or y is odd, okay, no matter what the other one is, one of these actually values must be odd, either the multiplication of x and y or their sum. Okay. No, exactly no, because what we wanted to show is that either this one is odd or the other one is odd. Okay. So this completes the proof by contrapositive position. And okay, so note that our use of without loss of generality within the proof is justified because the proof when y is odd can be obtained by simply interchanging the roles of x and y in the proof we have given. So I think that out of precaution, mathematicians would give it a try very quickly and would show that, okay, so it really does not matter. So, but you should think about it, okay? So just instead of writing the proof, okay, you just say without loss of generality, and it's good to give it interpretation since the rule of x and y and the property is interchangeable. Good. The last proof method, I think, is backward reasoning, okay? And backward reasoning is sometimes quite useful. It's like when you are asked to prove something by inference, okay? It's good to do it backward, okay? Instead of thinking about all the facts that you have in hand and all the possible ways you can combine them together, it's better to think about the final result that you want to reach and to check if you can get it backward. It's yeah, sometimes it's not very insightful, but still, if you can do a few steps backward and a few steps forward, okay, you may meet in the middle. Okay. This type of reasoning, called forward reasoning, is the most common type of reasoning used to prove relatively simple statements. What we did with direct proofs, actually, it's called forward reasoning. But sometimes forward reasoning is often difficult to use to prove more complicated statements. Let's check an example. So actually, the reason backward, to reason backward to prove a statement Q, we started from Q, okay, and we check the implications of this fact. So what if Q is true, okay? If you want to prove Q out of P, okay? So maybe Q has too many elements or facts in it. So we start by analyzing Q and drawing backward the premises that are required to make a Q true. And then you will see that all the ingredients needed to prove Q exist already in P. But simply it was not clear from the first side, okay? You have a very nice example here. Show that the arithmetic mean, x plus y over 2, of any two positive real numbers, x and y, is always greater than their geometric mean, which is the square root of x times y. The only premise here is that x and y are positive real numbers. Okay, so if you start from x greater than 0, strictly greater than 0, and y strictly greater than 0, how can you prove that x plus y over 2 is actually always greater than square root of x times y? It seems very difficult to proceed with a direct proof. But if you start actually by analyzing this inequality, so let's do it with one note. Okay, so if we want to prove that x plus y over 2, I'm sorry. Okay, so if we want to prove that x plus y over 2 is strictly greater than square root of x times y, then what does it mean? Okay, let's proceed backwards first to check the point behind it. Okay, so can we prove this? The question now is, can we prove this just given the fact that x is positive, okay, strictly positive, and y is strictly positive? Okay, if you start with those two facts, okay, it seems very hard to reach this in equation. But let's start with this one. And I agree with you. If we calculate the square of both parties, you get something like x plus y square over 4 is greater than x times y. Okay? Sorry, which is actually greater than 4 times x times y. Okay? And you unfold the left-hand side, and I think you can get something in the middle. So it's x squared plus 2xy plus y squared greater than 4xy. Okay? So, well, this is equal to what? Or equivalent, sorry, to what? To x squared minus 2xy plus y squared greater than 0. But this is actually x what? Square greater than 0. Okay? So if you have x and y positive numbers, you subtract them, you calculate their square. So, okay, it must also be positive, okay? But we couldn't see the link, okay? So who would have thought about this? Just starting from x positive, y positive, subtracting them, okay? So doing it backward first helps you actually clearly in seeing the link between them, okay? So I think you have the details here in the slides, and you have the famous any question slide. Okay, so next time on Tuesday and Thursday, we will work on sets, okay? And you will see that there is something quite nice with sets operations, the union intersection, okay? And how to prove that two sets are equivalent. We will use the same concepts of logical equivalence to prove equality between sets, okay? So this is the last part. Even if we don't have recitation sessions on them, okay, you will see because they are quite similar to predicate logic reasoning and propositional logic reasoning, nothing prevents us from having a couple of questions about them in the exam, okay? But of course, the big part in the exam will be about classical logic, predicate logic, equivalence and inference, plus proofs, okay? And exercises about proofs will be uploaded in a few minutes from now, okay? So I'll upload them, you will work on them, you will see them during the recitation, we will talk about them in the class if needed to prepare you better for the exam of next Monday, okay? Sets may be included in the quiz, yeah, even if you don't have recitation sessions on them, because the underlying methods to prove facts about sets can be found either in logic and predicate logic or in the proof of logical equivalences. Yeah, to prove that two sets are equal, let's say the intersection of B and C is equal to the complement of the union of their complement. Well, this is like proving P and yeah, it's like De Morgan's law applied twice. Okay, so something like that. Okay, or De Morgan's law applied on negated propositions, something like that. Okay, thank you guys.